All right, here we have testing for our photodiode TIA. Here's the circuit. We have our photodiode here. We can see that we have a 5-volt regulator here that's powering, giving power to the circuit. We have a laser here that is being driven by this square wave. So it's gonna be pulsing at the same frequency as this. And you can see the laser here, right there, coming here and hitting the photodiode. Now we're getting power in here and everything is going on here. Now the voltage out is being read here in this green wire by the oscilloscope down here. And you can see here the blue is the input wave and the yellow is the output wave. So we can see we have a clear signal that we're receiving and measuring based on this photodiode.
Here I'm testing the DRV8825 motor driver. Here is the board set up and it's plugged in. I have the stepper motor, 12-volt power ground. This ground is connected to an Arduino I'm using to drive it for testing. Have stepder enable, and then I'm pulling sleep and what's the other one? Reset up to 5. Not right now, because it'll just start moving. I'm gonna connect this to 5 volts, and it drives stepper motor.
So this is a testing for our variable TIA. Here we have a laser and our power meter that we're going to use. This PCB here is our TIA that we're going to use. It has 4 stages. The first with a basic amplification, and then 3 more stages after that with increased amplification. So here I have our laser going into our power meter. We can see at this point there's only about 30 millivolts coming out of this. So when I add a second stage, let's see. When I add a second stage here, I have these LEDs to show which stage is on. We see we get an increase of about, now we're at almost 400 millivolts. I can increase this again. I get this untangled. And add another stage. Now we see we're almost at 4.5 volts. Our supply for this is 5 volts, so we're really close to saturation. So I'm going to cut the power down with this linear polarizer. And so now with this stage, the power should be cut down, and we're back down to about 330 millivolts. So adding the third stage, or the last stage, will increase this even more. And I can test this. And we're almost at 5 volts again now. So you can see that each stage of this is adding more amplification, and it's working exactly as expected.
All right, here we are successfully programming the STM32 via a USB to UART bridge for the first time to enable the USB DFU for further programming and data transfer. All right, now we've uploaded the USB DFU program, and now we can access the board through the USB port.
So this is the setup that we have right now for our system. All these parts are borrowed because we're still waiting on some of the parts that we're getting for our full system. But this is an example of what the setup will look like. Here we have a 980 nanometer laser that the user will have to align to these 2 irises. This is going to be the reference for the whole system. So the laser goes through here, through these 2 irises. Here we have a linear polarizer to set the polarization of this laser as it comes in. And then we have, this is the 2 polarizing elements of the polarimeter. You have the rotating quarter wave plate. The stepper motor here is going to drive the quarter wave plate to rotate it. And as it rotates, it passes through the linear polarizer, which changes the power output. And as it goes through, here we have a lens that will focus the beam to come around here and go into this power meter. And we're going to measure the power as it rotates here. So as we rotate, you're going to see the quarter wave plate rotates. It's going to rotate a full 180 degrees. Okay.
So this is the STM running its code for 180 loop and taking EDC raw values, converting it into power, and sending it to the Python GUI. So it's taking sample for every step. We have it set for 800 steps right now. And at the end of this loop, it will give us a plot of the Stokes parameters. And then it will have the calculation for the Stokes parameters. Okay.
Here are the results for our polar emitter testing. We did several different tests. Here's the first one. You can see that there is a clear sinusoidal, and we report the Stokes parameters. This is for test 2. We get a very similar result, and test 3 as well. And then here is a average of, here's a report of all of our different tests, as well as an average on standard deviation. The Stokes parameters are not accurate to what we actually got because we haven't been able to calibrate our sensors yet. This is just because time constraints, as well as the fact that our parts aren't here. We want to calibrate for the parts that are going to be for our final system. But what's good to know is that these results are relatively consistent, and so if we needed to do a simple average, we could get a pretty straightforward and accurate result.
So here we have our beam profiling set up. We have 2 servo motors, one in the X direction, one in the Y direction, scanning across our power meter. You see here it goes slowly and takes measurements at each step, and then goes back and does it again. And this will allow us to do multiple scans over different parts of the beam.
Here's a little presentation of our beam profiling results so far. So these are some of the early results. We have 3 different plots: the plot versus angle, the knife edge, and then derivative of the knife edge scan. The plots look okay, but our results are way off base. The calculations need some working on. So some of the problems with our data calculation, as you can see, we're not getting the correct results. Our beam width, which is the D sigma, is around 2.0025 millimeters, but it should be around 5 millimeters with the laser beam we're using for testing. Here's another screenshot of one of our other test results. This scan had better plotting results, but our beam width calculation was still way off. As you can see, the D sigma calculation is about 20 millimeters. The result of this is probably likely the Python code, so I need to find a better method of calculation. And then our latest beam profile results, our scan for this one was a better result plot-wise, and the calculations are actually pretty accurate with a slight difference. This one shows around like 6 millimeters when it should be around like a 5 millimeter mark. And the plots of the derivative still needs to work on, but it is the latest scan that we've had so far.
So here is the part of our demo that is for the microsynth interferometer. This is what we're using to measure the wavelength of the laser. We have the same IR laser here and the 2 irises that will be used, the user will use to align the laser. There's going to be a movable mirror that we're going to insert in here that's going to direct it to this beam splitter. And here we have 2 mirrors, this one and this one. This one is controlled by a stepper, and it's moving the mirror, and then the return signal will be read by this photodiode here. Now our laser is not really powerful enough to be able to see it on its own, and we're still probably going to need to incorporate more gain into our photodiode circuit, so we don't quite have an exact measurement yet. But if you look really, really closely, you can see there's a slight interference pattern there. You're interfering with the beam there. You can see a slight interference pattern there, and as it moves, it changes. It's really, really hard to see right now, but if you look closely, you can make it out.
So going over some of our current issues and troubleshooting that we've been having to do. To begin, we had a lot of issues with our beam profiling. The servo resolution is probably maybe not as good as we want it to be. So we're going to explore potentially a different motor or hopefully just a different way to collect the data that will have us have better resolution. So for example, we're going to try just moving the servo at a constant speed, and if we can sample really fast, it should hopefully avoid the issue of the degree resolution on the servo. So that's our main issue currently with the beam profiling that has prevented us from moving forward with our M squared measurements and our divergence measurement. For the interferometer measurement, though, um, a lot of the lasers that I was using just weren't coherent enough or they weren't powerful enough to really get a good alignment on the interferometer. So I need to talk with my sponsor about getting a better laser to analyze. Additionally, for the alignment, the movable mirror wasn't as accurate as we hoped it would be. So we're going to explore getting a beam sampler that will have a more accurate alignment. Additionally, the photodiode TA didn't have as good enough gain as I wanted it to be, so I'm going to have to replace the feedback resistor and potentially make the gain variable to accommodate for different powers in the in the interference signal. So that will allow us to have our broad power range that we want, but also still be able to read the interference pattern. And additionally, with the smaller beam sizes, we want to do at least a minimum of 4 millimeter beam size. So most of our lasers, this is another issue to get with our sponsor about, but most of our lasers are much smaller than that we had to analyze. So we're looking for a better laser, but one thing that will help with the interference pattern is if we can have a lens to expand the beam. So we can investigate a negative focal length lens that will blow up that interference pattern and allow us to see um, the pattern better. But this, though, um, implies that we need a lot more gain on our photodiode TA than we were expecting. So that's some of the issues we're going through and we're troubleshooting for the interferometer. Next, for the polarimeter, we had some issues of timing between the stepper rotation and power reading. We got pretty good with it, but we're going to investigate to see what the best exact data collect procedures are going to be for getting accurate Stokes parameters. And then finally, of course, we need to calibrate it so that our TAA and quarter wave plate rotation um, can have exact power readings and exact angles so that we can have the best and most accurate calculations we can get. Finally, there was some issues with our noise. Some of the ADC readings were a little bit noisy. So we're going to analyze one of our TIAs to see if it's from the TIA or if it's from the laser. We're going to need to figure out where that noise is coming from and see what we can do about it. And then finally, for the motor drivers, we noticed that some of them were, some of our purchased ones were doing okay, some of them weren't, but ours that we designed and we built, they worked, but they heated up very quickly. So we're wondering if the current is a little bit too high. So we're going to investigate potentially a higher voltage source that will reduce the necessary current value. Um, but that is what is on the horizon for our problems and how we're planning on solving these problems moving forward.